to the production team. This next segment will primarily be focused on work done on the paper, but there will be a moment where I'm going to bring the textbook in, and you'll need to, of course, cut and paste that out for any annoying little pauses and all that sort of thing. I will try to make sure that I do not speak over anything important that is going on when I flip pages. I'll try to create pauses for you. Okay, so let's get ready to begin. In the last vignette, we looked at this joint relationship between two variables and defined what joint marginal, conditional, probability distributions were, and we worked with a couple of two random variable kinds of examples. Here we're going to get into covariance, which in itself measures the potential linear relationship that exists between two random variables. And by the time we're done, we'll broaden this out to multiple random variables as well, at least in some sort of context. Right? Your textbook and lots of others will use the symbol sigma sub xy, which right off the bat should tell you something about when we're talking about measuring linear relationship. We're also talking about something about spread, right? Because this is real close to that symbol for standard deviation or for variance, and it is related in many ways. So it's not just about a linear relationship, it's also about measuring when variables are real close or real far away to the mean simultaneously. And so let's look at this a little bit more closely here. Some people will use the symbol for covariance, capital C, lowercase ov. Some folks use all capital COV. Some people will use all lowercase COV. That's what your text does. I don't care for that myself because coefficient of variation is sometimes C period, O period, V period, all in lowercase. So I like to stay away from either that and use either capital COV or capital C, capital O, capital V. I know that's ridiculously confusing, and I wish there was another approach to it. I can't solve all the problems of the world. All I can do is alert you to the potential for falling into some confusion. Right, so we're looking at the covariance between two random variables, x and y, and that's going to be defined as the expected value of x away from its own mean and y away from its mean value. Right, so what this is really doing for us is trying to get to some sense of when x is real far away on a large side from its mean, is y also real far away from its mean on its large side, or vice versa, small and small side being away from the mean, or is it possible that x is real large away from its mean in a positive sense at the same time that y is real far away on a small side, as a negative side, away from its mean? Which side of the mean? Do those happen in any sort of a linear kind of relationship? And we'll have a number of examples here that will graphically show combinations of x and y and what the typical covariance will be, and later we'll normalize that into the correlation coefficient. And once again, we could, just like we did before, break this out as using this linear operator and multiply all this out and then get collect like terms and that sort of thing. And when we do that, we'll find out that this could also be written as the expected value of x times y minus the mean of x times the mean of y. And this is a calculation from here to here that you should be able to do quite readily, and might be a great little simple problem for an exam. Right? And this is literally expected value of x times y. And this form is oftentimes a lot easier to work with when you're processing data, if you're going to go through brute force kind of approach, whether it's by hand or setting up a spreadsheet calculation. Of course, there are lots of tools out there that will do this covariance calculation between two sets of data, paired data sets, quite easily at the push of a button. And beginning of the next module, we'll actually start to talk about using one of those, besides Excel, just using something called Minitab. And that's an alert to you, too, that you should make sure that you have access to Minitab through the Northeastern website. All right, so let's look at calculating the covariance for our instrument accuracy problem, that traffic counter problem that we were doing before. Right? We had that collection of actual number of vehicles in a 30-second interval and then that which was recorded. And here we've got our marginal values for the actual number, our marginal values for the recorded numbers, and we're going to use those here to come up with this expected value of x, y minus the mean of x minus the mean of y. Right? And previously, we've already, for that traffic counter example, determined what the mean of x was. That was 1.3. It was on average 1.3 cars per 30-second interval were arriving. Right? And we didn't show the calculation or perform the calculation for the mean of y, done in the same kind of fashion as what we did before, and that turns out to be 1.15. So that makes sense, right? We were, in our example, we were always having more actual cars arrive than what we were counting. And there's your two average numbers. We also need to obtain the standard deviations here as well. It will turn out for reasons why you'll see in a moment. And the standard deviation for x is 1.1, and the standard deviation for y is 1.12, and there's some digits that go on there. I encourage you to work that out on your own and see if you can come up with that using probably the notion of the expected value of x squared minus the square of the mean is going to give us the variance, and we take the square root of that, and you end up with that number right there. Okay, so that number is those parameters are going to be useful to us here in a second. You can see why these two are. You don't yet know why those are going to be valuable. And so let's go look at how we determine expected value of x times y. And that is literally nothing more than we're going to take as a sum our x value, our y value, and the probability that each one takes on those values. And so that means really we have a double sum over all x and all y. Okay, so if we flip back to our table, then we'll take 0 times 0 times 100 divided by 40. There's your probability mass, 100 divided by 400. Right? And of course that's 0. And then we'd have 0 times 1 times 16 over 400. And so on and so forth for all these. And obviously we have a whole lot of zeros. Right? And sum up all of those weighted products, right? Because that's what all this is this times that is the product, and that's the weighting, how likely that those occur, the probability mass. If we do all of that, then for our data that we have from our traffic example problem, our expected value of xy is going to be 2.56. So the covariance of xy is equal to 2.56 minus 1.3 times 1.15. Right, and that will be equal to 1.065. A fabulous number that has units of x times y. Unfortunately, don't really know how to interpret what a covariance of 1.065 is, just like I don't know how to interpret what a standard deviation is. Right? Is 1.1 large? I don't know. Depends, remember, on how that compares to the mean in that case. So our normalizing condition there led to the COV, coefficient of variation, being the standard deviation divided by the mean, was 1.1 divided by 1.3. That was how we normalized and had some sense of the relative dispersion that we were going to end up with. Right? We aren't going to use exactly that kind of thing here, but it's a similar notion of that we're going to normalize this, and we're going to do that with a concept called correlation. With the symbol rho, right? And that's our correlation coefficient. And rho, by definition, is equal to the covariance between two random variables divided by the standard deviation of each. Right? So instead of dividing by the mean of each, we're dividing by the standard deviation of each. And in terms of some slightly different symbols that turn out to be a little bit nicer to use, sigma sub xy divided by sigma x divided by sigma y. Right? And that's why we use this symbol sigma here for the covariance, because it's related to the standard deviations here, and that makes a nice, simple, easy to remember kind of expression. Right? And so for us in this example then, we'll have a positive covariance of 1.065 divided by 1.1 and 1.12. Again, that 1.12 actually goes out a few digits. And that number is going to be 0.86. And 2 goes on for several numbers here. And the correlation coefficient actually tells us quite a bit. You'll learn at some point that this 0.86 correlation coefficient is going to, when we square it, tell us how much of the variation in one variable is explained by the variation in the other variable. In this case, 0.86 squared is about 0.74. So 75% of the random variation in y is explained by the random variation in x. And remember, x is our actual causal random variable here. It is the one that is that we're actually trying to measure, and we would expect a fairly strong correlation between the two, right? Because one random variable is the measurement of the other. Okay, let's look at this in a slightly different kind of way, and that is that our rho value has bounds that we can show between +1 and -1. And they can take on values in between. And these are absolute bounds that rho cannot be any greater than +1 and can't be any less than -1. And it turns out then that partly because of this notion that I haven't proven to you, but I've said in words, this notion that what we really care about is rho squared, if that's what it sort of explains our significant elements there, that here at 0.5, both plus and minus, then any correlation number between those two, we say that we have a weak linear correlation between those two random variables. The other crucial breakpoint is at about the 0.8 and -0.8 region, where in here we say that we have a moderate linear relationship between the two variables, and then the remainder, if we have correlation coefficient between 0.8 and 1, plus or minus, then we have a very strong linear relationship, and it is only purely and totally a measure of linearity between the two random variables. And that's exceptionally important to take note of. In terms of your textbook, here's where you see the same expression and derivation that we were just talking about. And here's their use of the lowercase symbol of COV. Again, I don't care for that because that gets confused with coefficient of variation. I either capitalize that or I use a capital C, lowercase OV. Or I really prefer to use that symbol right there. When we turn that page over, in figure 5-13, let me stop, let everybody catch up. If you turn the page over to page 172 in your text, note that in figure 5-13 we got 4 different scenarios running around. In this first one, notice that this pairing of the x and y data is such that that general cloud creates a relatively linear trend from lower left to upper right. In other words, if I wanted to throw a line in there that somehow best fit this fuzz, it would be one that would have a positive slope. Hence why we have positive covariance, and we would have a fairly large correlation coefficient in this case. Fairly large meaning something greater than 0.5, and I see this is sort of tightly packed and a strong linear trend. I'm going to guess that this is probably around a 0.7 to 0.8 correlation coefficient. Okay. Whereas when you look down here in the lower left, that while we still have this linear trend, it's just that it's in a negative slope kind of fashion. Hence you'll have a negative correlation coefficient. Okay. When we look at this one here, though, this is, although it looks like a very definite square pattern, the thing to recognize is there's no significant linear trend that's at work in this one. Hence that would have 0 covariance. Right? And probably also no real systematic functional relationship between x and y. Right? So in that case, knowing something about x really has no contribution or influence about y. Whereas when you come down here, on the other hand, you have a very distinct relationship between x and y. It's the circular pattern. Right? So knowing something about x likely tells me very much something about y. Now it's a little goofy because if I'm right here in x, it could be a plus y up here and it could be a minus y down there, but there's very much a distinct pattern that's at work. Okay? That's crucial because note that from a covariance standpoint, there's no linear relationship to be found here at all, so you have 0 covariance. However, there is a very distinct fundamental mathematical relationship between x and y. So from a stochastic independence standpoint, we would find that these are very much dependent random variables. But the covariance, on the other hand, would be 0. Ooh, that's a really goofy kind of idea. And before we go in and dig into that one too much further, because we're in the text and we're right here, I want to go to one more page. And that's the facing page. And notice here again we see this definition of the correlation coefficient in your text, and then down below you see the limits that we have here, and a little bit of a hand-waving argument in the text about why that has to be. We're simply going to allow you to take this on faith that this is absolutely the case, and we can demonstrate it later on. It's left to the reader to derive that result themselves, right? Not particularly important for us to be able to derive these bounds, just simply note that those are the bounds. So if you're doing a calculation and you for some reason come up with a correlation coefficient that's -5, there's something wrong in the calculation. You might have taken the reciprocal, who knows, there's a lot of ways that you could have made a mistake somehow, but those are the very explicit bounds, and these are meaningful physically to us, as opposed to if you just tell me the covariance number all by itself. I don't really know how to interpret that other than a plus means something, a minus means something, but a plus 0.1 does not mean that I have less or more covariance than a number of plus 5, for instance, because I don't know what that's out of. Right? And that's what I need to know. How much is it out of? And that's what the correlation coefficient, in essence, is going to do for us. So let's reset here, production team, and get ready for some more work. So let's take a closer look at this notion of covariance, and let's do that in the context of a function. And this is going to be a context that's going to turn out to be quite useful for us when we get into the next series of chapters. So let's let Z be equal to X plus Y. So X and Y are two random variables. Right? And rather than start thinking about what the joint probability distributions are and that sort of thing, let's instead just ask questions. Well, what would be the mean of Z, and what would be the variance of Z? And of course the mean of Z is the expected value of Z, and now we can substitute in that that's the expected value of X plus Y. Right? And of course you can break that apart by the linearity of the expected value operator, and so now you end up with that that's the mean of X plus the mean of Y, a very intuitive and good feeling result. If I were to put a constant here, AX, that wouldn't really change anything other than I'd have an AX here, an AX there, and of course it's a constant, so it can come right on out, and you just have A times the mean of X. Again, a nice, satisfying, intuitive type of result. Yeah, well, what about the variance of Z? And this is where we're going to see something different and surprising show up that turns out to be crucial, and it of course connects right back to covariance. And it also explains a little bit about why I was talking about the notion of what does rho, the correlation coefficient, do for us. Right? So let's go directly here and substitute in. If we want the variance of Z, that is the expected value of Z away from its mean squared. And we know that that's also the expected value of Z squared minus square of the mean. And now this gets into straightforward manipulation here, and it gets a little bit lengthy, but we're going to substitute in X plus Y for Z, and I'm going to go directly to the next step, which is to expand that product. And so that'll be the expected value of Z squared is the expected value of X squared plus 2xy plus y squared minus, and then the square of the mean of Z. So that's just this thing also broken out. Don't forget to put your minus signs on each one of those terms. All right. And now I'm going to rearrange some things here. Right? Because expected value of X squared can go along with the square of the mean of X. So I pulled the first term here and the first term there. Right? And then I'm going to go and do the Y term as well. And then I'm left over with these mixed product terms. Right? So we'll have plus 2 times expected value of X times Y minus 2 times the mean of X times the mean of Y. Right? So that first term is the variance of x. And the second term, of course, is the variance of y. And the third term is, of course, plus 2 times the covariance of x and y. Right, and note, if we slightly change our notation here, that's sigma xy, right? Then, and take note that while g, rho was equal to sigma xy over sigma x times sigma y, then I can rewrite this finally that the variance of z is equal to the variance of x plus the variance of y plus 2 times the correlation coefficient between x and y times sigma x times sigma y. That's a important result, a very important result here. Right? And what it says is that, hey, the variance of the sum, right, is going to be given to us by the variance of one plus the variance of the other. But if we have a correlation here going on between x and y, that's going to also contribute to more variance in the sum, right? If x and y are unusually large together at the same time, it's going to increase the spread that we have back here in the y. On the other hand, if we have a negative correlation, that x is real far away from the mean on the large side, at the same time that y is real far away from the mean on the negative side, well then these will counterbalance each other, right? And that will tend to reduce the spread in z. Those are crucial kinds of ideas or applications of the notion of the correlation coefficient, and you can see them right here. Right? One more idea before we close off this discussion, and that is to ask the question, does independence imply no correlation, and vice versa? Does no correlation imply independence or dependence? What does that mean? And so for that we have to go back a little bit here. Let's look at the expected value of x times y again. And let's put that in the context of a continuous random variable. Right? And the expected value of x times y is literally the value of x times the value of y times the probability that they both take on that value. Right? And if we're in the continuous world, we're going to integrate over all x and over all y combinations. Right? And that's just the normal standard all-encompassing formulation for the expected value of x times y when we have a joint distribution. Now if x and y are independent, remember that means that the joint is equal to the product of the marginal. Right? I know I still used f here. The subscripts are all important. These are two different functions, and that's different for that one, so we really have three different functions that are sitting here. Right? And when we substitute in, then we get integral of x times y fx times fy dx dy. Right? Remember, these are truly and totally independent, which means that this fx is not a function of y anymore, right? So it can be pulled out, and we can segregate terms here that are just about the individual functions. Right? And so here's a critical result. This is equal to the mean of x, and this is equal to the mean of y. Right? So now, if they're independent, the expected value of x times y is going to be equal to mean of x times the mean of y. Remember, the covariance between x and y equals expected value of x times y minus the mean of x times the mean of y, and in this case, with independence, that's equal to 0. Right, so one crucial result is that, yes, stochastic independence does mean no correlation, no linear correlation. Right? However, the reverse is not true. No correlation, or zero correlation, zero covariance, does not mean stochastic independence. It means there's no linear relationship between the two random variables, but there may be a nonlinear. And go back to that circle problem that we showed in the book before as a perfect example of that very case.